Welcome to the first episode of the Physics Society podcast series, PhysPod. Our first guest, whose appearance coincides with the International Celebration of Women's Day, is Professor Anita Ho-Baillie. Anita is a John Hooke Chair at the Nanoscience Hub of the Sydney University. She's a world leader in photovoltaics and perovskite solar cells and has achieved various awards and efficiency records with her research team. She has also been recently granted the Royal Society of New South Wales Award for her leadership in her field. Speaking with a female role model such as Anita was very much mind-opening. We focus on various topics from her research and career up onto the very philosophy of life. Please do inform us about your reception of this podcast idea and do not hesitate to reach out at any point. And here is our conversation with Anita Ho-Baillie. Anita Ho-Baillie, you are the John Hooke Chair of Nanoscience at the University of Sydney and identified as one of the leaders in advancing perovskite solar cells with over 18,000 citations. Welcome to our first episode of the Physics Society podcast.
Thanks for having me, Marnie and Angela. I've been in the University of Sydney for 3 years, since 2019. So I came in December 19, just before COVID started. And we built our lab during COVID, which was interesting. And we've been doing a lot of solar cell research in our lab. So we've got 2 labs in Sydney Nano Hub and also another lab, at the different parts of the campus. So we've got a good team where we involved in solar cell research and also research in perovskite materials, looking at the application of the materials for maybe photosensors, X-ray detectors, and what else? Field effect transistors. Also, we're collaborating with people in the chemistry, also utilizing the perovskite cells for solar-driven hydrogen production, also using them for magnetic optical devices. What else do we do? Also, we have expanded the application from land to space. So thanks to some of the really great undergraduate SSP projects and TL projects, so we were able to start a brand new research for space applications.
Perfect.
A lot of applications.
It's very interesting scientific problems, a lot of challenges that need to be overcome, but it's very good because we're able to engage students in all these interesting topics and expand our mind a little bit so that we're not just doing one thing, but doing multiple things. And we also found that if we do multiple things at the same time, we can transfer the learnings from one research area to the other one.
Yeah, perfect. So I'm going to go a bit further back and I'm going to start very much, if you'd like, even earlier than high school. But tell us about your interests. And I guess that's for a lot of people, that's where their scientific career even starts. So your high school education, university, and from there on, maybe tell us about that section of your life.
Sure. I liked and good at maths. And I think in the HSC, I did physics, chemistry, and maths, all the typical subjects that an Asian student perhaps would do. And then I pursue engineering. And during my second course, when we were doing electronic circuits, that one of the professors, late Stuart Wenham, he introduced us to solar cells. So basically a PN diode work in, so it's not work in reverse, so it's still working as a PN diode, but instead of just passing light through by electrical bias, the bias is actually produced by the sunlight. So the light will excite the electrons from the valence band to the conduction band in the semiconductor device, and therefore generate a current. And that current, instead of using power, is actually generating power. So it was really interesting. And then he took us to the rooftop of the building and show us a solar panel and show us how the solar panel can power water pump by just simply removing the cardboard that's shading the solar panel. So I was absolutely fascinated by that because there's no PowerPoint. You're not plugging, anything into the PowerPoint. So I was well and truly fascinated by this free energy source from the sun. And then I did my thesis, my undergraduate thesis project on solar cells. So what I was doing was simulating the effect of swapping solar cells in the panel to see if it's possible to improve the efficiency. And then, and also I had a co-op scholarship. So I was able to work in a startup during my 5th year of my engineering degree. So the deal is we'll get the scholarship, but in return we'll work for a company in our final year. So I had a really, really good time. So I was involved in actually automating one of the plasma enhanced chemical vapor deposition system. Mm-hmm. And I felt that I was contributing. We were able to automate the system so that they can do R&D faster. And then what happened? Then I decided to do a PhD, encouraged by the late Professor Stuart Wenham, and also my parents. Wouldn't it be wonderful? We have a daughter who's a doctor. So I did that, and in my first year PhD, we actually went to Nepal to install a solar power battery system, just really simple one. So lead acid solar power battery system for a medical clinic in a very remote area in Nepal. And I think it served 30,000 people in the village or in the vicinity. And it was just amazing how much, a small solar system can improve the lives of the local people. Just very simple things like latrines, running water, electricity for them to be able to switch lights on at night when there are patients coming, or women in labour needing help, and for the medical doctor to provide help. That is just amazing. The impact and the difference you can make using renewable energy.
Yeah, I've always been interested in how we can, apply physics in a more material sense rather than just staying in the theoretical. So I really love seeing what you've done here. So you've come a long way. It's really, really inspirational. So I know you're currently in the field of photovoltaics and perovskites, if that's how you say it. Mm-hmm. Do you want to tell us a little bit more about how that works?
Yeah, sure. So photovoltaics is basically photoelectric effect. As I said, you have a material that is a semiconductor, and it becomes a conductor when you provide enough energy into the system. So you have electrons that can be excited from the valence band to the conduction band, and thereby you generate what we call the photogenerated currents that can be harnessed. And perovskite is a type of semiconductor. It's basically a description of materials that's got a certain crystal structure. So it's actually in the, naturally occurs. We have perovskite, oxide perovskites, and I think it's actually one of the most common crystal structure you can find in nature. Though the perovskite that we're interested in is the metal halide perovskites. It's got organic materials and also metal halide. So sometimes they call it hybrid materials. So it's not just inorganic elements in the crystal, but also organic elements. So what makes it so special? So it's been discovered in 1890s, and people have sort of tried to describe what the material is. And then people were looking at possibly using it for LEDs. So LEDs is solar cells in reverse. So you supply the electricity and then it gives out light. Whereas for solar cells is you use lights to generate electricity. So anyhow, what makes the material, so they were looking at it for LEDs, but what makes the material so interesting is it's actually got very good optical absorption coefficient. So you can have very, very thin layers of perovskites in the order of maybe a few hundred nanometers, and you can absorb the light to produce that photoelectric effect. So compared to the incumbent technology, for example, the silicon cells that you find on your roof, they're around 1 micron, so it's around 100 to 200 times thinner than the incumbent silicon solar cell. So they're around 100 times thinner than the piece of hair. So that makes it very exciting because we can apply the materials on flexible substrates, and we can apply on applications that require lightweight, for example, space and vehicles. Also, it can be made using a solution process. So, for example, with silicon, you need to purify it from quartzite. So it goes through many steps of purification. So, and we're looking at 1,000-degree temperature, whereas for perovskites, you just need the chemical precursors to be ready, and you can coat it onto a substrate and form the thin film very quickly, within minutes, and you give it a very low temperature treatment, for example, 100 to 200 degrees. So it's got the thermodynamics of forming that film is, not as taxing as the silicon. So that's what makes the material so interesting. So all the labs around the world who are interested in photovoltaics are also researching on this material. Also, it's a compound semiconductor. So it's unlike silicon, where it's just made up of one element. You only got one fixed band gap. So the band gap is the gap between the valence band and the conduction band. So it's the energy you need to excite electrons from the valence band to the conduction band. So for silicons, it's 1.1 eV. So any photons with energy above 1.1 eV will be able to excite the electrons in silicon to make it conducting. For perovskites, you can tune the band gap from 1 to 2. So that means with photons that are of higher energy, they can be utilized better. So you don't have that wasted heat. So for example, if you have UV light that is around 2.3 eV, for example, if you use it to excite silicon, it does the work, but that extra 1 eV will get wasted as heat. But if you use it to excite say a 2 eV perovskite cell, then it's utilized fully, so it doesn't get wasted as heat. So what happens is you can stack perovskite of high band gap on top of perovskite of mid band gap, and then on top of perovskite of low band gap, and you create this sort of multi-junction structure or multi-junction tandem. And you can improve the efficiency from a theoretical limit of 30% to 40% for 2-junction tandem to 50% for 3-junction tandem. So you can see that, wow, because you're not losing the excess energy as heat, you can improve the solar cell efficiency by, a great extent.
Yeah, so based on what you're saying, then it seems like there's good efficiency and improvements happening in terms of the results. I'd like to know how much of this application is also reflected in the market and the industry at the moment, outside of research and development, and where do you see this prospect to be, perhaps?
Yeah, so the material is very exciting. As I said, you can stack it on top of silicon, for example, to improve the efficiency of the silicon. So, there are various startups who are trying to commercialize the technology, but one of the challenges is the stability. So as I said, thermodynamically, you can form the film easily. And does it mean thermodynamically, the film can degrade easily as well? So in our labs, we're also trying to make the cells more durable, make perovskite materials more durable. And there's various ways of doing that. So for example, we found out that the perovskite materials can be degraded by heat. And actually what heat does to perovskite is it can actually, because it's got organic materials, it can make the organic materials outgas and leave the system. So one way you can suppress that is to have, is to protect the cells by packaging. So to make sure that outgassing does not occur, when you do that, when you actually stop the outgassing from occurring, it's funny that you can actually suppress the degradation. So that's where multidisciplinary research is interesting, because we actually use a technique called GCMS, gas chromatography mass spectrometry, where we use that technique. So what is used for? Usually used for pharmaceutical, used for detecting drug cheats, used for analyzing maybe soil sample from Mars, and we use that to look at perovskite cells. So many people are like, oh wow, like it looks so obvious. It's only when you start doing it that you go, yeah, we just never thought of putting this technique with perovskite. So anyway, that's what we managed to do. But we also look at how light can degrade the cells as well. And at the moment, we've got a body of work that we are about to publish. So I'll probably let you guys read it when it comes out. But also there are other ways of perhaps stabilizing perovskites is by manipulating its structure. So at the moment, the high performance ones are sort of made up of this 3D array of crystalline structure. But one way of stabilizing it or engineering its properties is to slice it from this 3D structure into layered structure. And when you do that, you sort of terminate the edges with materials that you want to create a more stabilizing force on the material. So that's what we're doing as well.
It's interesting how many aspects, I guess, of design go into it, rather than just thinking about the material in of itself.
Yeah, we're also talking to people like in the School of Chemistry, where can we infuse or incorporate metal organic frameworks, for example. So for example, we're talking to Professor Deanna in chemistry. Can we combine two different classes of materials, maybe to solve a problem of each type? So maybe you can infuse or incorporate a MOF into perovskites to stabilize the structure, or you can incorporate perovskites into MOFs, maybe to engineer some of the optical or maybe electronic properties. So yeah, it's really exciting.
Yeah, now we're gonna zoom out a little bit, attack the more general questions. Do you think you could tell us what makes a scientist? What qualities do you think you might have?
Yeah, I think follow your curiosity. Be curious. Don't be ashamed of it, and don't be ashamed of asking questions as well. I think when you're young, you can afford to ask as many. Actually, when you're older, you should anyway, because no one knows everything or all the answers. So you just be brave in terms of asking question and trying to find out answers to the questions. I think that's really important for anybody in their career, really, but I think especially in the scientific field, scientific research, because advancing knowledge is really important for the field. Also follow your passion as well. I think when you do science, you see an outcome. You may see an outcome in certain fields, whether it's in quantum computing, whether it's in renewable energy, zero emission economy, or whether it's in medical science. So follow your passion. If you think that you want to make a contribution in a certain sector, in certain industry, just follow that and then see what science can be used to make your contribution.
Yeah. But what you mentioned earlier, which is very interesting to me, was the fact that you say you have to ask more questions when you're younger, and then you also change it as it's obviously you should ask questions all the time. But I feel like there is an incentive that kind of limits your ability to ask. Not necessarily the ability, actually. Maybe how busy you get is a factor in it of the questions you ask. But could you tell us about that, like for yourself and generally what you think? Is it a quality of science perhaps that kind of, as you move on, get more advanced in your field, it kind of doesn't let you ask as much curious questions anymore?
Yeah. Are you expected to just know because you're a scientist?
Yeah, I
Mhm.
think people have that expectation.
Yeah.
And what I do now is in group meetings, I just tell the group, can I ask a stupid question? And I guess it disarms everybody when I say that, right? And they go, oh, well, of course it's not stupid. So I still ask questions, and I would still say, sorry for my ignorance, can I ask? And I think the good thing with science is it actually sometimes you don't have the answer straight away, and let people around you to know it's okay. Because I think sometimes the lecturer or student staff dynamics is they expect you to know the answer, and then the research setting, you also want them to find the answer, but then sometimes we actually don't have the answer, but that's why we're doing research. So I think engender that culture that is okay. So what we do sometimes is no one has the answer in the room. Then we go, well, why don't we just allocate this research question or initial question to A and B, and then next time they come back and report what they can find. And it's really, really helpful for everybody because we're all learning at the same time. And I think having gendering that culture that it's okay to ask questions and it's even okay to not have the answer straight away is a good thing.
I guess as a woman, it's a small cohort of other women that you can turn to. And I know we shouldn't be afraid to reach out or whatnot, but it's still a feeling that you have. I don't know if you've gone through that. I guess, do you have any general advice for women in physics and science in general to work around this?
There are lots of nice guys out there.
Yeah, for sure.
And
at least hope so.
Yeah. And I think women or men, boys or girls, when they mean, they can be just as mean.
Yeah.
So I think having women around you also helps because there are issues in life, or there are things that apply to women that don't necessarily apply to men. So it's good to have, women who are very supportive. So yeah, feel free to go and find those support. Reach out outside of your school if you have to. But again, there are also lots of great male colleagues. So I think I get both. I get support from both gender. So I think just don't be afraid to reach out and say, I need help. And I think people will become disarming immediately if you say, well, I need help, and they will be very happy to help you. Those who don't help won't help anyway. So actually it can be the other way around. When I was in uni, I just back in the days when we didn't have much internet, I just get a lot of phone calls from male students who need help. They will ring me, and I know this, 10 o'clock at night, the phone will be ringing. So it could be both ways too.
Yeah, I guess it's not that much difference when you look at it in more detail.
Yeah, in a grand scale, it's not really a bunch of differences, and you're really looking at qualities of humans rather than something like gender that separates you that way.
Yes, that's right. That's right. And I think just be comfortable in your own skin, believe in yourself, pursue what you really like, what you really love, and try to do your best. I think there are people who said do the work, not just the job that you're passionate about, but the stuff that you're good at. So if you're naturally good at maths and physics or certain subjects, I think you can keep pursuing that because it does make it easier if you're good at something too.
Yeah, so with an introduction to this idea of women in science, and with celebrating the International Women's Day as well, I'd like to know your view on the role of women in STEM at the moment. Obviously, quite frankly, there is in at least this area of physics still an inequality, at least, of men and women in the field, at least in terms of representation and demographics. But where do you see that at, and where do you see the perspective, or at least where do you want it to be?
I think it does depend on the language being used. describe things. So, but I also find that in some areas it's not true. For example, in medical physics, you may find there's more women being represented in medical physics. You may find women more represented in renewable energy, more so than you think. So, and perhaps it also, the interest also builds on the value systems that people have. And there may be areas that certain gender may feel sort of more appealing to them. Yeah, it's an interesting topic because people have been talking about how we teach subjects that will appeal to both gender. And there's quite a lot of work being done in school physics as well. And I have to say, this school is one of the most caring schools I've worked in. They genuinely care for students. They do the teaching so well, and there's so many exciting undergraduate projects as well. So I think, without advertising, I think you guys are actually in a very good school, in a very good place. The Faculty of Science in the University of Sydney is just amazing. The level of teaching and the quality of the teachers are just amazing.
Yeah, I think maths is also doing a really nice job in, I guess, promoting the advanced streams to female and like gender diverse students. Because like when you say the word advanced, like this sense of imposter syndrome just grows so much. So they're like reaching out to the students individually and providing mentor programs, which I think maybe something we could take up. It's really great initiative.
Yeah, and I heard the statistics, the female representation goes down. For example, when they in primary school, they think maths is just as hard or easy for girls. And then as they progress, they think that maths is harder for some reason for girls. During when you want to move on to senior roles, for example, women have to take care of family. So I think there are ways around it. For example, give men the same amount of paternity leave, and also maybe the way maths is taught, to be more discrete, using languages that are less abstract. And I think one of the tricks I play on my 11-year-old is I just always say maths is easy.
Yeah, my mom told me that too.
It seems to work at the moment.
Yes, so Angela mentioned something that I kind of ticked in my brain as well that I definitely wanted to ask. And imposter syndrome seems to be a common between not only, as I've realized talking to a few academics, that not only among students, but also academics.
Yeah.
So if you could tell us about how imposter syndrome plays a role in your life and people around you, perhaps.
Yeah, I think it's hard. In a sense, it could be harder for academics as well. For example, with grant application, the success rate is around 20%. You can write a really, really amazing grant proposal, and yet you can still be rejected. And you're already like one of the best. Like you were probably one of the brainiest. In a Christmas party you go to, you're probably one of the brainiest. Also, the way we disseminate our results, we publish in journal articles that is peer reviewed, and you come back with at least 20 to 50 questions. You got to improve on the quality of the manuscript. Probably you have to redo some of the work. So you're constantly bombarded with criticism. You're constantly bombarded with questions. So it could be hard because it can sort of put a hole in your ego. But I think you just have to keep going and have a really balanced view of yourself and be comfortable in your own skin. And I think that is really, really, really important. And don't take things too personally. Sometimes people take things very personally, and they can either blame themselves or blame the reviewers. So I think just do neither. You're doing really well, but then some of the questions are valid, and see how you can address them. So yeah, I don't know whether I have really answered the question, but I think being comfortable in your own skin is so important. And also, I think sometimes we don't help ourselves, but then no career helps themselves. We like to aspire to the people who are successful, right? Like I never tell you, I would yell at the computer when the internet is down. I'll get very frustrated with my students. I'll have all these flaws that I don't show to people, right? But we're all human and we all have bad times. And I don't tell you necessarily all the grants that didn't go up, right? So you only see all my success. So if I list you the number of proposals I've written that got rejected, probably the list is a much, much larger, longer than the list of successes. So so I think don't just look at the service, look at the social media, go and talk to the real person, the real people involved, and hear their stories, hear their journey. And one of the things I like to do is hang out with older people because they've got so much experience and they're also a lot more forgiving and they have a rich experience. They know what is important and what is not so important. And I think for young people, getting a generation of young people that are more anxious. And I think it's because everything is important, right? Wow, they've got to do well at school. They've got to be an all-rounder. They've got to go and find a job. They've got to be able to support themselves. They've got to meet their parents' expectations. They've got to meet their peers' expectations. You got to be a triathlon and, be a geek at the same time. It's just impossible to do everything. So I think the experience from older people will really help, and just talking to them, and they'll just tell you, don't worry about that, Sometimes I say to my daughter, without letting the teacher hear this podcast, some of the things that get said at school, that the expectations that is on top of you, some things you can do, some things you may be able to do 50%, but you can't do 150% at everything. It's just way too much for you, and you have to set your own priorities. Some things you have to say no, some things you just a bit mediocre, and then follow the stuff that you really want to do.
Within all this, I guess, what keeps you with doing your work? Like what motivates you? What excites you the most? And I guess wakes you up every day.
Yeah, it's funny. It's actually the students too. Like the students that can drive me crazy. They're amazing. Like sometimes we'll have to, do a review of what we do. And I look at the students. Sometimes I look at the names and I chuckle because, all the funny stories, all the funny interactions, and some of the very frustrated people, they're actually really good. So I think it's the people do motivate me, but also I think the science does motivate me, the ability to learn new things. It's a very privileged job to be an academia, apart from all the, all the other stuff. You do learn new things. And, if you're someone who loves to learn new things, I think science and engineering is a really good career. I don't think there are many jobs out there where every day you learn something new. And also, you just have the privilege to be able to ask questions, to answer questions. So I think people who are writing grants, people who get failures, just keep reminding yourself you are in a very privileged position to be able to ask questions and answer those questions. And I don't think you get to do that a lot in other jobs.
Yeah, I think that's the great thing about science. Like you don't, there's no end point. You're gonna keep going.
Exactly.
Yes. And I think I love the communicating of the science as well, either to the scientific community or to the public. I also love that aspect, being able to excite people, to make them interested, and it's to arouse their curiosity. So I love that part as well. And I think most scientists will probably agree on that too.
So what kind of makes me curious about this question is, I would say, duality of ideas that we get from childhood. So as a child, and inevitably I'll talk about myself, when you start doing science, although it's amazing and you're curious about it as a child, your hope and dream one day is to be the Einstein of your field, to be written in the history, right? And as you progress, you see different endpoints, and everyone has a different vision at different ages and different experiences. Obviously, it's completely multifaceted. Obviously, as you mentioned, with your humanitarian work at Nepal, that sounded amazing. That sounded like a fully altruistic almost view of this, very, very similar to history. But also, a lot of times we do science just because we simply love it. I hope you agree with that as well, because as you said before.
Yeah.
It doesn't need to be one or the other, clearly, but what do you think? Which one drives you more, and which one should drive one more? Should it be an individualistic or a collective effect on the whole?
That's a really good question, actually. I love your last part of your question actually is the answer, right? So we can collectively have individuals that have different passions, right? And that is true in our teams anyway. There are people who all they care is the science, and you love that, right? You want to work with those people. And then there are people who just want to, world domination. They want to make a difference, completely passionate, but they also need to rely on their breakthroughs and the advances in science to make that impact. So I think you answer your question. I think we need teams with people who have different, drives that drives them, but also being able to work as a team to achieve big things. So for the person who really just interested in science to find new knowledge, and then for someone who probably interested in the impact and the translation to be able to capitalize on that finding.
Yeah, so it's more so about accepting science, not as just a tiny insular community of little nerds in their rooms, but we need to, I guess, we need to talk more. We need to collaborate with other disciplines.
I think so. And I think, we got so many big challenges in life, I think food, water, climate change. It can't just rely on one Einstein anymore. I think we need to have big teams of different talent, people with different talents and different expertise to work on these huge, big problems.
Yeah. And a flaw that I was thinking of is that as humans, we love stories. I think that's the truth. And the more exciting and rare the story is, I think we bring it up a lot more. So a story like Einstein's life or Newton's life, or people who've accidentally almost discovered things, always seems to get more attention compared to a rigorous, many years work of science that has influenced something. So maybe an effect we could have is to promote the general scientific method more, if you agree with that.
Yeah, I think every good scientist needs to have a good journalist behind them, right?
Yeah, exactly.
So to be able to help them to communicate the significance of the work and the impact of the work. And why do we want to do that? Because we know science is useful. Science can solve problems. But also, I think we all acknowledge that, science is also just part of the solution, right? If we can't convince maybe the politicians to make the right policies or to have the appropriate regulations for certain things, what we do is also not making a contribution as such. So I think it's not just science dominating the world, but I think being able to work with people who can communicate that for us, being able to work with people who can enact for us, to have that political will, and also, people also got to live and got to feed their children. How does it help in terms of the industry? How does it contribute in terms of the economy? So yes, we're just part of something big.
Yeah, well, science collaborative environment. We're trying to solve all the big problems. And it's all great. You're getting new knowledge, you're teaching new generations, but like, what are, I guess, some unpleasant aspects? We've left off on a high point, but what are some of the words you would say?
I think, as I said, being criticized all the time, or you feel you're being criticized all the time, that can be difficult. And sometimes, biggest problem is us, human people. We can be mean, and we can be not collaborative. We can have an ego bigger than we are. And so I think probably the same in every profession. Maybe less in science in some ways, because we also feel, like the imposter syndrome at the same time. So, and I think, for a lot of scientists, they always feel that they need more support financially to do the work. And I think for a lot of Australian scientists, they feel that they're not as well supported as they like to be. So, I think it's probably an ongoing problem. We just have to keep our heads down and then keep doing it, and maybe have champions for us who can advocate our work and be given the value of our work and be valued, and also be well supported for the work we do.
Like maybe one of the ways we kind of get this imposter syndrome is maybe the way science is taught as this sequence of grades. Like we've got Democritus, and then Newton, and then Faraday, and then Einstein. It's like, if we don't have any of these grades, what are we amounting to? It feels we compare ourselves a little bit too much, I think. It's probably something contributing to this pleasantness.
Yeah, and I think makes science less intimidating, because sometimes the way we speak about science can be intimidating to others. I think people feel intimidated about things because they don't understand, and perhaps to different people we can communicate in a certain way that they can understand at their level, and at their level useful enough for them to make informed decisions. So maybe for people who have the background, yes, you can tell them everything about, all the intricate details. But for people without that background, you just at their level, you communicate it to them so they know what to do. So they know that when they get the vaccine, they don't get, better 5G at home. Or they won't affect their children that will develop ADHD and things like that. So, so I think that will help both for the general public and also within the field to encourage people to have a bigger participation.
You mentioned criticism earlier, which as an unpleasant aspect. And very briefly, if you could tell us, in the scientific way, what does that look like? What is really criticism? Because if we're dealing with facts and logic, then criticism kind of becomes like a proof. You could prove something wrong, but clearly it's not just simply a proof, and people have different opinions and different views. So how does that look like?
Yeah, so you would think there's no opinion in science. There is. So for example, in my field, in what I do, maybe we'll submit a piece of work. What we usually do is we get at least 2 reports back. Sometimes you can get 3 to 5, and they will come back with a summary of your work, and they may come back with, say, 10 questions, 5 to 10 questions. So it ranging from some of them will say, I don't like the work at all. I have seen reports like that. I actually just don't like the work. I don't see the point of it. Or some people say, I love the work, but I just don't think the conclusions you drawn are based on sufficient evidence. Sometimes they may come back and say, why did you do it this way? Why did you measure a material properties using this technique? Why can't you use a different technique? Sometimes they may say, I agree with the technique, but what is the settings? Or why don't you use the technique for these kind of sample sizes? Or can you vary the variables using, like, perhaps according to my suggestions? And sometimes you will get somebody with a sort of like alternative motive. They may be your competitor, or sometimes you will get comments that are really useful. So then you've got to have that wisdom. Remember the wisdom I told you, people get anxious and anxiety because everything is so important. What do I do? And you can't do 150%. And I guess you need the wisdom. You probably need guidance from your supervisor to go, okay, this is a major point. Yes, we have to address it. This is somewhat slightly minor. And we can tell them we may not address necessarily the way you want, and you can explain it. Sometimes people come back, I don't like your work. I can't see any significance. And then you can either blame yourself as, oh yeah, my work is worthless, or blame them. Or maybe it's the way you write it. Maybe you just didn't highlight the significance enough. And maybe it's the same thing. It's exactly the same thing in the abstract. You just have to rewrite the whole thing and change the language and change the emphasis of the sentence. So this is when, you thank your English teacher because communication is so important. Being able to communicate the importance of your work, the significance of your work, the findings is so important. The way you put emphasis in the sentence, even the way you use comma is so important. So these are the criticism you get. And I think have a thick skin, see the issue, and that requires wisdom. And just have a priority. If you can't address everything, what can you do? And negotiating skill. You never think that being a scientist, you've got to be negotiating, and you need to. Sometimes you need to negotiate with the editor and say, look, I can address this and this and this and this, and I think I can address 90% of the work. Will you look at it now, and will you just tell me an answer whether this is acceptable? And sometimes they will go, yeah. And for some of the things they ask, I can't do, I don't have an access to an accelerator, and I don't have that, energy level, things like that. So yeah, you would never think that all the soft skills that, they teach you at school were so important. Being able to argue your point, being able to debate, and the social aspects, being able to negotiate, and even with your colleagues, have access to certain equipment, and a bit of give and take, the student and staff relationship. This person's got this personality, slightly different from that person. How do you bring the best out of people? So all these skills are actually important as a scientist.
So I was doing a bit of Twitter deep diving from actually 3 days ago, and I will read this out, and hopefully it's on the screen at some point. You just tweeted that have said no to 1 plenary, 2 keynotes, and 1 invited talk in the last 6 weeks, another one to decline. Sob, keep saying to myself, family is important. And that being said, I wanted to know, how do you manage, the time for yourself, work, and obviously family, given you have also a child as well as a parent? How do you prioritize those? How do you manage it?
Yeah, the wisdom, isn't it? As I said, have the priorities. Sometimes you just got to write everything down and ask yourself, is this really important? What is important in your life? So ask yourself what is important. And it changes with life stages too. So if you could travel without too much family responsibility, go for it. If you can't, there are some other things that are important. Just have to write it all down, and then sometimes ask yourself, if I don't do this, what's the worst it could happen? If I fail this, what's the worst that can happen? If I can't travel internationally, can I travel domestically? If I can't travel and I've got this weekend, do I sit in front of the computer or I go for a swim? I might as well make the most out of it. And I think, every day is, you got to make life decisions. Sometimes you fail, sometimes you make good decisions, sometimes you make bad decisions and move on. Don't have too much regrets, because it will make your life very miserable. Make a decision and then you just move on with it, and don't regret. because that was the best decision you could make anyway. So yeah, so that's all I can say. And I think you're too young to sort of worry about families yet. And every time there's a closed door, there's an open door somewhere. Yeah, so say yes to things as much as you can, but sometimes learning to say no could be a what is it? Sort of it frees you up, you know. Could be I don't know how you say it. It could be a release as well.
For sure, I think learning to say no is so important in setting boundaries. Like it's time after spending 2 hours on a problem. It's time to move on. It's time to give yourself time to let yourself dwell on it a little bit more.
Yes.
So very last one, if you don't mind, could you tell us about, I guess, a life-changing or influential experience you've had? If there's
it really can be anything. It doesn't need to be related to science. This is a very almost philosophical question.
I think that's quite a lot. I think coming to Australia is life-changing. Coming here as a teenager and then having to adapt. I think seeing that solar panel, you know, powering the water is life-changing for me in terms of science career. Having children, having a child is life-changing. Suddenly you go, wow, you know, you can do a lot of things. To have to go through so much pain, you go, oh wow, everything else is, just don't worry about it, roll with it, and don't overthink things. I think after having family, you can't overthink things, and that could be a good thing to everybody. Just don't overthink not anything, but don't overthink too much. Otherwise, it could be paralyzing.
Great. Well, thank you, Anita, for meeting us and having this conversation. Really thoroughly enjoyed it.
Yeah.
And yeah, any words from Angela?
Likewise here.
Yeah, it was very enlivening. Like, you never expect science to be such a social discipline. Yeah, you really need to, I guess, think about how it's not just acquiring knowledge and then moving on. Which, yeah, I guess I'm looking forward to that a lot more since still in second year.
Yes, so, and I'm looking forward to you guys joining the SSP project.
Yeah.
I'll do honors.
For sure.
Yeah, we'll work on the solar cells.
Yes.
Definitely. Well, thank you very much, and hopefully we'll see you soon somewhere.
Yes.
Yeah, we'll see you around.
See you in the corridor.
Yeah. Yes.
Okay, see ya.
Thank you.
Bye-bye.